Hi and welcome to my channel. Today, instead of a gaming montage, this one is a coding video. So let's start with the basics. Security teams already have tools that can tell them what cryptographic exists inside a binary file. They can generate CBOM files and inventory reports showing software contains AES, RSA, or SHA-256. But knowing what is present isn't the same as knowing how it is being used. Is AES running in ECB mode, where identical plain text blocks produce identical ciphertext blocks? And can reveal pattern in encrypted data. Is it the key that is hard-coded? Is randomness coming from a weak source like time? Answering these questions often requires source code access or manual reverse engineering. That's why I am introducing CipherFault. CipherFault is a crypto usage evidence engine for compiled software. It analyzes binaries, traces how cryptographic values are used, and produces evidence about whether cryptography is being used securely or not. The first thing I need is a binary with non-cryptographic performance. If I'm going to build a tool that detects crypto misuse, I need a ground truth dataset where I already know the correct answer. So I'm creating a very small OpenSSL program with a couple of intentionally planted security issues. First, I'm defining a static AES key directly inside the source code. This is hard-coded key, which is already considered a bad practice because anyone who can reverse engineer the binary can recover it. Next, I'm creating an OpenSSL cipher context and initializing AES. But instead of using a secure mode like GCM or CVC, I'm deliberately using AES in ECB mode. So at this point, we have intentionally produced two crypto misuses. One is hard-coded encryption key. The second is the use of AES in ECB mode. The rest of code is pretty straightforward. I'm encrypting some input data. You open SSL EVP interface and returning the encrypted output length. I don't want to manually type compilation command every time I make change, so I'm creating a simple makefile. I'm generating two versions of the same binary. The first one is a debug build, compiled with debug symbol enabled. This version preserves a lot of information about the original source code, making it easier to inspect and analyze. The second one is a stripped build. This removes symbol information and more closely resembles the binary you would encounter in the real world analyzing third-party software. Both binaries are built from exact same source code. The only difference is the amount of information available to the analyst. And the difference is actually important for this project. If CipherFault can only work when a symbol are present, then it's not solving a real problem. Once this binary are generated, the next step is to stop looking at the source code entirely and start working directly with the compiled executables. The first build failed because of a typo. After fixing the makefile, the build succeeded and we generate a debug version containing a symbol and source level information and stripped version where information has been removed. Now that I have binary, the next challenge is figuring out how to analyze them. For that, I am using Ghidra along with PyGhidra, which gives me access to Ghidra's analysis engine directly from Python. The first thing I want to extract is the control flow graph or CFG. A CFG represents how execution can move through a function and serve as foundation for everything that comes later. So I am writing a small script that loads a binary into Ghidra, locates target function, extracts a basic block, and then builds a graph network using network. At this point, I am not doing any machine learning yet. I am simply trying to answer one question. Can I reliably transform a compiled function into a graph representation that I can later analyze and learn from? Once that works, I can start building the rest of the pipeline on top of it. After a few debugging sessions and fixing some mistakes in the extraction script, I finally got the first successful result. Ghidra was able to locate the target function and extract its CFG and represent it as a graph structure. In this case, the function was very small, so the graph only contained a single node, but that was the important part. The important part was the proving that I could automatically lift a compiled binary into a graph representation using Python and Ghidra. Now, instead of encrypted records, all I see are labels, and that is exactly what we wanted. A machine learning model can't learn from a single toy example. I need a data. So instead of writing cryptographic implementation from scratch, I started pulling in real life cryptographic code. I chose Tiny AES for as a lightweight open source AES implementation. I downloaded the source file, added to corpus, and compiled it to object file. Because the build still contained debug information, I was able to see the function names such as cipher, key expansion, etc. Picked one of the core AES function, key expansion, and ran it through the CFG extraction pipeline. Unlike the earlier example that only produced a single node, this time the graph was much more interesting. The extracted CFG contained multiple nodes and edges representing a loop, branches, and actual structure of AES key schedule. At this point, I had been working with a small experimental script. They were useful for validating ideas, but they were something I could build an entire system on top of. So I started moving the functionality into proper project structure. The goal was to create a lifting layer capable of processing every function inside a binary, not just a single hard-coded file. For each function, the lifter extracts its block basics, collects the instruction inside those blocks, and builds a CFG connecting them together. Most importantly, it does not rely on function names. Whether the binary contains readable symbol or anonymous functions, the lifting process works exactly the same way. The output is a structured representation of binary that the rest of CipherFault can consume. This becomes the foundation for region extraction, feature generation, and eventually the machine learning pipeline. Once the lifting layer was finished, I wanted to see whether it can handle an entire binary instead of a single function. So I wrote a small test script that runs lifter against every function discovered by Ghidra and reports some basic statistics. For each function, I am extracting its CLG, counting its basic blocks, and collecting its instruction content with those blocks. And this was the first time I could see the structure of entire cryptographic implementation laid out in front of me. Functions like key expansion, cipher, mix column, and round keys were all being lifted automatically each of their own graph. At this point, CipherFault wasn't making any security decisions, but it could finally transform a compiled binary into a structured data that machine learning model could actually learn from. To verify the lifting process was actually robust, I ran the same experiment on two different tiny AES files. First, I analyzed the object file containing the debug information. As expected, the output contained meaningful function names. Then I compiled a full stripped executable and ran the exact same lifting pipeline again. This time, all of the names disappeared. Instead of a recognizable AES function, I was left with anonymous labels, but something interesting happened. Even though names were gone, the structure wasn't. The same function still had roughly the same number of basic block edges and instructions. The identity was removed, but the underlying behavior remained. And that's the key observation behind CipherFault. Compilers can remove names, they can strip symbol, but they can't remove the control flow and instruction pattern that actually implement the algorithm. Those patterns are what machine learning model will eventually learn to recognize. At this point, I could lift an entire binary and represent every function as a graph, but there was still a problem. Machine learning models don't magically know what part of function is important. And in optimized binary, a single function can contain multiple logic pieces of a code merged together by a compiler. So instead of treating an entire function as a unit, I started breaking function into smaller candidate regions. For the first version, I used a simple structure-based approach and strongly connected a component which essentially represent a loop in CFG becomes a candidate region. The intuition is that many cryptographic primitives spend most of their time inside the repetitive loop of structure. So if the function contains any multiple loop, each loop becomes its own region that can be analyzed independently. Running this against tiny AES immediately started producing meaningful results. Instead of seeing one large function, I was now extracting a smaller graph region that could eventually be used as a training sample for the recognizer. This wasn't the final region extraction strategy, but it was the first step toward turning the raw control flow graph into a machine learning data. At this point, I had graph regions, but I still couldn't feed them in a neural network. Machine learning models don't understand assembly instruction, function name, or CFG. They need numbers. So the next step was feature extraction. For the first version, I kept the thing intentionally simple. I built a small vocabulary of common assembly like MOV, XOR, add, sub, call, and a handful of others. Then, for every basic block, I counted how many times for each instruction appeared. This transformed a block of assembly code into fixed line numeric vector. Once every block had feature vector, I could combine those vectors with graph structure extracted earlier and convert the entire region into Python geometric graph object. The output wasn't just CFG anymore. It was now a machine learning sample containing node, feature, graph, connectivity, and a label. When I ran the pipeline, I could finally see tensor being generated for every extracted region. At the moment CipherFault had crossed an important milestone, I was no longer just analyzing binaries, I was getting actually training data for the recognizer. Now that I could generate machine learning samples, I needed something just as important. Labels. Model can't learn without cryptographic code looks like if every example it sees is cryptographic. So I created a small non-crypto corpus alongside tiny AES. The first file contains common string processing routines like strength, length, calculation, string comparison, string reversal, and word counting. The second contains mathematical algorithms such as GCD computation, Fibonacci generation, primality testing, and array submission. None of these functions perform cryptography, but many of them still contain loop, arithmetic operations, and CFG patterns that could potentially confuse a model. The goal wasn't to make classification easy, the goal was to force model to learn difference between cryptographic and non-cryptographic behavior. With both crypto and non-crypto example prepared, I automated the entire corpus generation process. Each source file was compiled multiple times using different optimization levels, then passed through the lifting pipeline, region, extraction pipeline, and feature generation pipeline. Every extracted region became a training sample with an associated label. By the end of the step, CipherFault had generated the first real dataset, 67 graph region in total, with 37 cryptographic sample and 13 non-cryptographic sample. For the first time, I had enough data to train actual model and see whether the core idea would work. When the dataset fully prepared, it was time for the first real experiment. I built a simple graph stage model and trained it on the graph region extracted from corpus. Nothing fancy, just enough to answer a single question. Can graph neural network learn to distinguish between cryptographic code and non-cryptographic code using only the information extracted from compiled binaries? The first few trial training runs were exactly what you would expect from any research project. Import errors, broken dependency, version mismatch, a lot of debugging. But eventually the model started training and supervising, and surprisingly it worked. On the small proof of concept data set, the model was able to separate cryptographic and non-cryptographic region with a promising accuracy. Now this doesn't mean the problem is solved. Data set is tiny, the evaluation is simplistic, and there are still major questions around the generalization, compiler, optimization, and real-world cryptographic libraries. But for the first time, there was evidence that the core idea might actually work. In the next video, I'll start stress testing these assumptions, expanding corpus, and finding out whether the model is real cryptographically structured or simply memorizing the dataset.